In the last video, we have proved that theta, which one is the angle of rotation divided by length of the shaft, is same as equal to gamma maximum divided by r. That is the maximum shear strain divided by the radius r. Is same as the shear strain at any radius r. That is the shear strain is a function of radius r divided by the same radius at which we are interested to know the shear strain, is also equal to gamma max divided by r. Now from this equation, gamma max divided by r is a constant value, and therefore theta by L is also constant, or we can say here that theta is proportional to L. It means that the length of shaft is more, then the value of theta is also equal to more, and if the shaft is shorter, then the angle of twist will be smaller. One of the assumptions that we are using in deriving the torsion formula is the material is elastic. That is, if we draw a graph of shear stress versus shear strain, then we are working in this elastic region. For this elastic region, we can have a relation between the shear stress and the shear strain, and the shear stress is given as modulus of rigidity G multiplied by gamma, that is the shear strain. Here G is called as modulus of rigidity. Now using the equation that tau is equal to G times gamma, already we have developed the equation for gamma here. Shear strain is a function of R is equal to the maximum shear strain multiplied by the radius R divided by the total radius equal to capital R. So what we'll do here, we'll multiply equation 1 on both sides by value of G. So we'll consider equation 1 and both sides will multiplied by G. In that case, we have modulus of GT multiplied by the shear strain is a function of radius r is equal to modulus of GT multiplied by maximum shear strain which occur on the outer surface multiplied by the radius r divided by the total radius equal to capital R. Now G multiplied by shear strain is same as equal to shear stress. So this total value will be equal to the shear stress at any radius r. So we'll write this as shear stress at any radius r, or the shear stress is a function of radius, and G multiplied by maximum shear strain will be the maximum value of the shear stress, that equal to tau max multiplied by r divided by capital R. So using the elastic constant of modulus of rigidity, we have developed the relation between the shear stress at any radius r will be same as equal to the maximum shear stress multiplied by the radius at which we are interested in the shear stress divided by the total radius equal to capital R. So shear stress as a function of R is always equal to the maximum shear stress multiplied by the radius R divided by total radius equal to capital R. So this one is also a useful equation. We'll label this equation equal to 2. Using 1 and 2, we can develop here the formula for torque develop. But from this equation, first we conclude here that the shear stress, which one is a function of radius r, is a constant value is tau max and constant value of r. So shear stress is directly proportional to the radial distance r. It means that if the value of r will be equal to 0, the shear stress will be equal to 0, and it will increase linearly from 0 to capital R. Similar to the bending stress. In the case of bending stress, one fiber will be in tension and other will be compression. As such, there is no tension and compression in the case of shaft. Rather, we have pure shear stress develop, and the shear stress value will be 0 at r equal to 0, and the shear stress is tau equal to tau max if r is equal to capital R. So let's first discuss here the distribution of a shear stress, and then we'll go for the formula for a torque. So one equation we have developed for the shear strain. So shear strain is a function of radius r is equal to the maximum shear strain multiplied by radius r divided by total radius equal to capital R. This time the any radius r is between 0 to capital R. So this range you have to fix first, and only you can apply this equation in the given range. Then the shear stress is a function of the radius r is equal to tau max multiplied by r divided by capital R. Clearly here the tau r is proportional to the radius r, because value of tau max divided by r is constant, that is the maximum shear stress divided by r is constant. So tau r is a proportional to radius r. This one is a linear distribution, and according to this distribution, if we have r equal to 0, then the shear stress, which is a function of radius r, is equal to 0, and if we have r equal to capital R, then we have the shear stress will be equal to R is equal to capital R is get cancelled here and is the maximum value of the shear stress. So consider here a circular shaft with a center at O and maximum radius is equal to capital R. At any radius R, we have shown here the shear stress, which one is shear stress is a function of radius R. And this shear stress will be equal to 0 at center. At center, we have radius R is equal to 0. And when we are on the periphery, we have shear stress will be equal to maximum. So this value indicate the maximum value tau max. And check the direction of the shear stress. The direction of shear stress will be same as the direction of the externally applied torque. If we want to show the shear stress on the vertical line, then again at center O, we have shear stress equal to 0 at radius R is equal to capital R. We have maximum value of the shear stress, and at any radius R, we have shear stress is a function of R, which one is given as tau max into R upon capital R. You can show the shear stress distribution anywhere, as we suppose you select here this radial line. At center again we have shear stress equal to 0. At capital R we have shear stress will be equal to maximum value. Only thing that you have to show is that the direction of the shear stress and the direction of the torque will be remain same. At any radius R from the center, we have shear stress is a function of R. So the shearing stress as a function of R, and it varies linearly as we move away from the center. Now from this equation 1 and equation 2, we are able to develop the relation between the shear stress and the torque T. So over this radius R, our shear stress is remain constant. So for any concentric circle, the value of the shear stress is remain constant. So to show the shear stress here, you can use any circle here, and you have to just draw the tangent to this to represent the value of the shear stress. If you draw the tangent here, it will be the shear stress at radius equal to R, and the value will go on decreasing as you approaches towards the center. So this concept we'll use here. And secondly, we have the shear stress multiplied by the elemental area, that will be equal to our shear force. So we have dF is equal to tau multiplied by dA. Then this force is at a radius equal to R, so it will develop the torque, that will be dt is equal to dF multiplied by R. Once we get the elemental torque, then we can integrate it over the entire area, and once we integrate over the entire area, we can develop the expression for the torque is equal to T. So now our goal is to develop the relation between the shear stress and the torque. General distribution of a shear stress is known to us. Shear stress, which is a function of radius R, is given as tau max, that is the maximum shear stress multiplied by radius R divided by total radius equal to capital R. So this one is representing the total radius equal to capital R. We want to develop the equation between the torque and the shear stress. For this one, we will consider here one section, and backside of this section we'll use for development of the relation between the shear stress and the torque. So let's cut this shaft using this section plane. So we'll show here the resisting torque equal to T, and this torque is opposed by the shear stress on this face, and I have shown here concentric circle, and we know here that the shear stress, which is a function of radius R, is equal to tau max multiplied by R divided by R, is a linear distribution. At center it will be equal to 0, and it will go on increasing as we move from center to the outer surface equal to R. So this one is our distribution of the shear stress, which one is a linear distribution. In fact, here the shear stress value will go on changing from center to outer periphery. So we can solve this problem by integration method to find out the total torque. For this one, we'll consider here one elemental ring at a radius equal to R and area equal to dA. Over that area, the shear stress is remain constant. So this torque, which is acting in a clockwise direction, is opposed by this torque on this face, and we'll consider here one elemental ring of area equal to dA. The direction of this resisting torque you have to show in opposite direction, and all this shear stress is the same value and is given as the shear stress as a function of radius R is equal to tau max multiplied by R divided by capital R. Now this elemental area is a very thin area, and therefore we assume here the shear stress over this area is almost remain constant. stress multiplied by area will be the force. So this elemental ring which has a shear stress equal to tau r, area equal to dA. Here dF represent the elemental shear force, is dF is given as the shear stress which is the function of radius r multiplied by the area dA. Now this value of dF will going to change as the radius will also change. So first of all we'll calculate here the elemental torque. So let dt represents here the elemental torque, and therefore the value of the elemental torque is simply equal to the elemental shear force multiplied by the radius r. So we have dt is equal to df multiplied by r. Let's replace here the elemental shear force equal to shear stress which is a function of radius r multiplied by dA multiplied by r. This value of the shear stress which is a function of radius r can be replaced as tau max multiplied by r divided by r, and then we can integrate here to find out the total value. So let's substitute here the shear stress which is a function of radius r is equal to tau max into r upon capital R. This r I will write first and then we'll write here dA. This r into r is r square, and we get here tau max divided by r into r square multiplied by dA. So just integrate it and solve it over the entire area A. So I will continue with this equation. So let integrate here to find out the total torque. So we have total torque is equal to T is nothing but the integral of dt, that is same as equal to tau max divided by capital R. So these are the constant value multiplied by r into r is r square multiplied by dA, and we'll integrate it from 0 to the total area A. In this equation the tau max by r is a constant value, so let's take it outside the integral. We are left here torque is equal to tau max, that is the maximum shear stress which occur on the outer surface, that is radius equal to r, and we are left here with r square into dA. Now this equation is somewhat familiar to you, is nothing but the polar moment of inertia. So here we introduce the integral r square dA, which is nothing but the polar moment of inertia. So we'll replace the quantity integral r square dA from 0 to A, from 0 to A will be as equal to j, which is again equal to integral r square dA from 0 to A. This one is called as the polar second moment of area, or is called as the polar moment of inertia. So hence we are able to develop here the equation of the torque, and in this case we get the total torque T will be equal to tau max divided by r multiplied by the polar moment of inertia j. Let's say this one is equation number 3. So we can write this equation as tau max, that is the maximum shear stress, is nothing but total torque multiplied by the radius r divided by the polar moment of inertia equal to j. So let's say this one is equation number 4. Now we can put the tau max in the equation of shear stress, which one is the function of radius r, that is in equation 2. So we'll just replace here the value of tau max. So we get here the shear stress which one is the function of radius r is equal to tau max is replaced as the total torque T multiplied by radius r divided by j multiplied by again the r divided by total radius equal to capital R. Capital R and capital R will get cancelled, and here we have shear stress which one is a function of radius r in general is given as the total torque multiplied by radius r divided by j. So we have successfully developed the equation of the shear stress. So we know how to calculate the shear stress at any radius r, which one is given as total torque multiplied by the radius equal to r, where we are interested to know the shear stress, divided by the polar moment of inertia. Polar moment of inertia I take for entire area. Again this equation is valid from 0 less than equal to r less than equal to capital R. Here equation 3 we can rearrange, and we can write this equation 3 as total torque T divided by the polar moment of inertia j is same as equal to tau max, that is the maximum shear stress, divided by the total radius equal to capital R, and is same as the shear stress at any radius r, or the shear stress is the function of r divided by the radius r. So this again proves here that the shear stress is a linear distribution over the entire cross section. And finally, we'll develop the relation between the shear stress, the torque, polar moment of inertia, and the angle of twist theta. Throughout the chapter here, we are going to use this equation. So remember this equation. This equation says that the total torque divided by the polar moment of inertia is equal to the maximum shear stress divided by total radius equal to r. And if you are interested to know the shear stress at any radius r, you can use the last term. In the number of situations, we are using the solid shaft, and for solid shaft, the polar moment of inertia is given as pi by 32 d to the power 4. For solid shaft, the maximum shear stress will occur at radius equal to capital R. So at this point, we have R is equal to capital R is same as equal to d by 2. And now we can use this equation to develop the equation for torque. So we have torque is equal to tau max multiplied by polar moment of inertia J divided by the radius R. So let's substitute for J is equal to pi by 32 d to the power 4. This R will replace as d by 2 and we'll get a simplified formula. So we have torque is equal to tau max multiplied by pi by 32 into d to the power 4 divided by d by 2. So 32 by 2 will be 16 and one of the power of d will be decreased, that will be q. So finally we are getting here one very popular formula that I am continuously using for finding the value of the shear stress when the torque is given in the case of solid shaft. So we left here with pi divided by 16 multiplied by the diameter q multiplied by maximum shear stress. And this maximum shear stress must be less than the allowable value of the shear stress. So we have tau max will be same as equal to the yield stress in shear divided by factor of safety. So you can confirm here factor of safety using the simple equation of a torque, which is given as pi by 16 into d cube multiplied by tau max. Now consider here a hollow shaft with the inner diameter equal to d1 and the outer diameter equal to d2. So this value corresponds to the outer radius that equal to tau 2 at diameter equal to d2, and this value is same as equal to tau max, that is the maximum shear stress always occur on outer fiber. There is material here between d1 and d2 only, so we will to show the shear stress here between the limit of r1 and r2. This value corresponds here to the shear stress equal to tau 1, that is for the inner radius. And this time we can use this equation, that is tau, which one is a function of r divided by r. So from this equation we can develop the equation as tau max, which one is same as equal to tau 2 divided by tau 1 is equal to, if I take a ratio, it will be equal to r2 divided by r1. So one objective question can be formed here. They will give the value of tau max and they will ask you the value of tau 1. So use a linear distribution, or you can use the two similar triangle, and using the proportional limit we can calculate what is the shear stress at the inside radius equal to r1. As far as the polar moment of inertia is considered for hollow shaft it is given as pi by 32 multiplied by outer diameter d2 to the power 4 minus inner diameter d1 to the power 4. Here I will take out here d2 common, so in that case I will get pi by 32 into d2 to the power 4 into 1 minus we have d1 by d2 and whole power is 4. So let's substitute here the k, which one is a constant here, is nothing but a ratio of the inner diameter to outer diameter. In that case we can rearrange this equation as polar moment of inertia for hollow section equal to pi by 32 multiplied by d2, which one is the outer diameter, power is 4 into 1 minus d1 by d2 is k, so we have k to the power 4. Again we can develop this equation here of a torque. So we have torque is equal to maximum shear stress tau max multiplied by polar moment of inertia J for hollow section divided by the radius r. Now remember here it's a function of r, and tau max we have written r, so maximum value of the shear stress will occur at the diameter d2. So that value of r will replace as d2 divided by 2. And now we can substitute for polar moment of for hollow section, and we can simplify this equation. So we have torque is equal to maximum value of the shear stress tau max, polar moment of inertia will be equal to pi divided by 32 d2 to the power 4 into 1 minus k to the power 4, and again it is divided by d2, and these two will multiply, so we'll multiply by 2 and we'll divide it by d2. So one of the d2 will be get cancelled, it becomes d2 cube, and 32 and 2, so 16 is left. So this formula is almost analogous to this formula, so that is why we have arranged this formula in the form of k. So we have total torque in the case of hollow shaft will be equal to pi divided by 16 into d2 cube, that is the outer diameter cube, multiplied by 1 minus k. K is nothing but d1 by d2, which one is always a fraction, multiplied by maximum shear stress equal to tau max. So this formula you can use for hollow section. Now in this equation, if I put k equal to 0, in that case we have a same formula. In the case of a very thin circular ring, that is for a tubular shaft, so this one is called as tubular shaft. In that case, the polar moment of inertia is given as 2 pi r cube t, where r is the mean radius. This mean radius will be same as the inner radius r1 plus outer radius r2 divided by 2. And t represents here thickness. Here also we get a thickness t. So if I show the thickness t, then the value of thickness t will be same as equal to d2 minus d1 divided by 2. So thickness t will be equal to d2 minus d1 divided by 2. So sometimes they will give the thickness, so indirectly you have to calculate either d1 or d2, whatever is given to you. Commonly they will ask you the question based on the solid circular shaft to find out the value of maximum shear stress, or in the case of hollow shaft to find out the value of tau max. So remember these two equations. In the video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.